production was made in USA. No, it's not in China, so you should charge them more.溝通。So I'm a monkey, and you are bee. So I'm the monkey, okay, one.我觉得这费用。Okay. 去找chairman. Outside with chairman C, but inside he'll be a chairman. Ben.黃色。都要嚟幫手。
Okay, maybe we start now. Thanks for coming, and maybe I introduce briefly about our organization before we go into details. This event is organized by Artificial Intelligence Hong Kong, which is an entity, it's a limited company, and we right now have around these figures, close to 3,000 followers in Facebook and 900 something in Meetup. And we gathered about 156 experienced engineers, which most of them are the AI engineers or quantitative, financial. So today, I think most of the audience are from the financial industry or from from engineering, from science park, from IBAN, from a lot of them. We can talk to them, mingle. So last time I was the speaker here, and moderator was Carl. And this time I'm the moderator, and Carl is the speaker. So one of you may be our speaker as well. So because all of you are expert in different areas, so we just facilitate this kind of platform to give a platform for everybody to have a chance to talk about their expertise. So maybe you, the speaker, if you would like to be the speaker, maybe contact Carl, Eugenia, or me, so that we can arrange the talk in a good way. I'm Fred Wong from AI Hong Kong. I'm the co-founder of the company. Today my response is a bit slow because I slept only 4 to 5 hours last night. Why I sleep so little? Because we published a book about AI last night, which is this one. The signature color is black and white, and red, same with our logo. This book already available in Amazon. A pocket size, $9.9 US dollar. In case you are interested, you can buy one. This is talking about AI, how to use AI to explain blood type. The blood type, OA or AB or B. Okay, I'm not going to elaborate, but this is a very interesting book, fascinating. So our mission, a lot of people attend our event and ask what is our mission or what we are going to do. So our mission is to form a community to gather AI engineers, to form an ecosystem. And because we are in a financial area, so we relatively more focus on a bit bias on the financial side as well, because we located in Central. Our office also in Central, near Man Yi building, around 5 minutes walk from here. So we have 4 founders, our chair lady, Eugenia, chair lady, and Kyle, and one of Rex. Rex is not free today, and me. Okay. Few days ago, we found Andrew started his new career after leaving Baidu. He launched a company called deeplearning.ai. So deeplearning.ai is his flagship domain, I guess. And actually, several months ago, this is the photo took around I think last December, last year. We already applied a couple of domain. That's why Andrew maybe he's crying because he found those domains already occupied by Eugenia, which is machine learning.ai and image recognition.ai. So this is and we organized a lot of events in our office and here, including Kenneth Zhao, which is ex-Goldman, around 10 years trader, to talk about the AI trading. Around 3 to 4 months ago. And then Ray Zheng is a professor in CTU, talked about the AI, talked about last time here. And also from Huawei, a guest speaker from Huawei, Lawrence. Carl was the speaker to talk about, this topics about AI or fintech. Fintech, yes, fintech, yeah. This is me. And also talked about AI last time. Okay, we organized a lot of events before. So this around 8 events already organized, and we also conduct a lot of casual meetup. Also we attend the TensorFlow, Udacity, to talk about. We organize an event in SocGen, in the office of SocGen and BNP, to organize, to talk together a group of engineers to do the AI programming. And we have some sort of regular happy hour drinks usually in IFC. Oh yeah, this is totally explain. This is SocGen office, and the drinks party, TensorFlow. this is rework, in Causeway Bay rework office. Small group. So we have small group gathering and big group gathering, and also online will be the machine learning.ai. Right? So feel free to visit our machine learning.ai domain. It's already worth around more than $1 million for that for that website. Okay, that's all for my brief introduction, and I'm going to welcome the first speaker, Jonathan Yan. Jonathan Yan is the founder and director of the Real AI Limited, which is a Hong Kong-based AI research company dedicated to ensuring that humanity has a bright future with safe and beneficial AI. Jonathan obtained his master's degree in math and business research from Stanford U, and worked in the financial industry for a few years before transitioning to AI in around 4 years ago. Right? Okay, so maybe give a round of applause to thank you.
Thank you for attending this event. The topic of my talk today is the future of artificial intelligence. It's a big topic, but the message is actually very simple. I have only 3 main points to say. So if you're really busy today, just make sure you understand these 3 points. That's the gist of my talk, and then later I'll elaborate on those 3. So first is about the impact of AI. It's going to cause a lot of changes in our lives, and probably more so than many people have imagined. And I'm going to talk about why later on. And then the next topic is about timing, and finally I'm going to explain what we should do, given the current state of AI. So this is where we are today. The world is becoming more and more intelligent. If we look at the history, we're at a high point. This is a recent screenshot of my iPhone. All these very common apps, they all use AI in one way or another. Over here, the newsfeed, when we use Facebook or WeChat over here in Hong Kong, many of the posts or information that are pushed to users, they are actually selected by artificial intelligence algorithms. Similar algorithms are used by YouTube, Netflix, or online shopping so that they can better predict what you want to buy and hopefully make more sales. Images, these are some fun apps that can make your selfies look better or look more funny. There are also apps that do the reverse. So the better looking selfies, they turn back to the original so that people can actually tell the truth behind that service. On web search, Baidu and Google both use artificial intelligence algorithms to get search results. And also chatbots is one of the most popular areas for AI application. The problem is over here is they're going to get more and more intelligent chatbots that can answer questions and to interact with users in a very intelligent way. Oh, sorry. Okay, thank you. Yeah, and in transportation, AI algorithms. In robotics, there are real-life robots that use AI algorithms to roam apartments and do some things just like very little cute animals can do. In finance, there are AI algorithms that decide what stocks to buy and sell. It's been there for quite a long time. It's a robo-advisor for portfolio management. Even chess and calculator, they used to be considered artificial intelligence as well when they were first invented, but not anymore because now we know very well how they work and they don't look that smart anymore. If we look at the history, there have been many things that people used to feel that only a human can do, such as picking stocks, playing chess, do some housework, or even recognizing simple images, simple objects like cat or dogs or everyday items. But this list is rapidly shrinking. Recently, it is expected that Amazon, for example, is going to roll out quite large-scale supermarkets that they only need 3 human employees to run, and all the rest will be done by machines. It's not there yet, but it's coming. Today, we don't yet see machines can make a movie by themselves, or can really do difficult household work. But we don't know how long this will stay exclusive as human territory, because the history has shown us a lesson that this list is rapidly shrinking. The boundary between artificial intelligence and the natural intelligence is not that clear. So let's take a closer look. So what is artificial intelligence really? All these examples I showed earlier, these are narrow AIs. If you look at the apps, each app can only do a particular job. You can't just tell the iPhone, say, I want to do something new. How about prepare a talk for this one? Then you actually have to pull the right kind of apps and do that talk. I'll use a more famous example, AlphaGo. We all know that AlphaGo is a very good Go player, a Go playing system. It can beat human champions. But you cannot ask AlphaGo to play chess, because it only knows how to play Go. You can't even ask AlphaGo to play 5 in a row, even the stones look the same. You can't even ask AlphaGo to play a simpler version of Go that is played on a board of 17 by 17. That's smaller than the size of the Go board, which is 19 by 19, but AlphaGo will have no idea how to do, even though this new game will be much easier for expert human players. So that's what I mean here by narrow AI. They're really narrow. They can only do the thing they're supposed to do. But, well, let's again look at this earlier example with all these apps in the iPhone. What if, over time, we build thousands of apps, or even tens of thousands of apps, so that anything you can think of, you can easily pull an app and do what you want to do? Then that iPhone, if you look at the phone as a system, is actually very general. That's closer to the kind of general AI system that people have imagined and have expected for many, many decades. Because general means the app or the program or the system is not confined to a narrow range of tasks, but can do many, many things. A general AI chatbot will have common sense. For example, if you ask today's chatbot, let's say, the trophy doesn't fit in the suitcase. Which one is bigger? Which one is too big? Is the trophy or the suitcase? You see, this is a very easy question for humans, but very hard for computer, because the computer has to understand the common sense about trophy and the suitcase, their spatial relation, and decide which one is bigger. This is hard for computers to do, but very easy for humans. Once chatbots have common sense, it's going to be as easy for computers to do. So how do we get things more general? Just looking at this picture, the narrow AIs are usually done by very explicit programming. They're called symbolic AIs. But we can build on symbolic AI, and instead of coding up very explicit solutions or rules to solve real-world tasks, we can actually tell the computer how to learn from data. And that has the potential of being general. If the computer has a very good learning algorithm to just look at the data and extract what's in there by itself, like what we're doing today using neural networks, then we can move very fast from the range of narrow AI to general AI, and maybe even super AI or super intelligence. That's when machines surpass humans in intelligence. I'm going to show you a path towards that. So I'm going to start with some videos on games. So, fun time. So this is a very classic game called Meetup. It's very simple. You have a paddle at the bottom, and the goal is to destroy as many bricks as possible over here. Initially, this learning system doesn't know anything. It doesn't even know how to play. It doesn't know the point of the game is to catch the ball. But after a few hundred episodes, it starts to learn to play better. There is no explicit rules in the learning system that tells that this is the breakout is the game that is played. All it knows is the visual input, exactly as what you see over here, and a general direction of maximizing the score. After 600 episodes, it not only plays this game really well, it actually can discover tricks to make it very easy to play. And the trick is to dig a tunnel on the side so that the ceiling becomes a partner with a giant paddle and helps you destroy a lot of bricks. What's impressive over here is not that a computer program can dig tunnel. That's very easy. If you just tell a computer, this is what you want to do, this is what you should do, and the computer will do that because it follows rules. What's remarkable over here is that this trick, very effective at winning this game, is discovered by the computer itself. And this is a system that doesn't even know beforehand that breakout is the game it's supposed to play. If you wire this learning system to different kind of games, it can similarly discover rules or even tricks that win the games. This is done in 2013, and there was a paper published about that in 2015, so it's fairly recent. And the game gets better over time. Last November, this is a newer version of this gaming environment, where the environment is a lot more complicated. It's a 3D simulated world. It probably looks easier for players, for human players, because all the agents are doing are very commonplace tasks, just navigating, moving around, but it's actually more difficult for computers, because first, this environment is much more complex. You look at the texture of the walls, you look at the complexity, you look at the variety of items. This is a lot more complex cognitive task for the computers, but it's very easy for humans. Also, over here, the agents have more degrees of freedom. It can move around, it can change its viewpoint, it can even tag. This is actually the equivalent of shooting, but we want to develop friendly AGI, so we don't use the word shooting. We say tagging. So this is tagging items and to win points. So this agent has a lot more degrees of freedom. This is, by the way, done by DeepMind, and this is some screenshot of what's inside the agent. So there is very complex structure, but I won't go into details here because of time. Let's just go into a more advanced version. This only came out earlier this month. So this agent, again, is a 3D simulated world, but you can actually tell the agent what to do by enter a command in English. It's plain English. It's not encoded English where the machine translates back to English words. It actually understands the command as it is. So when you say all green object, the agent will go to all the green objects it could see in those rooms. It needs to explore all the rooms, look at all these items. And some items it has to wait until like the TV turns around so that it knows it's green. Like this one, picks a magenta object in the green room. That involves looking at the color of the room. Just look at the floor, oh, that's green. So where is the magenta object? Over here, that's the magenta object. You touch the magenta object and you complete the task. These tasks, again, they are very simple for humans. These are like baby tasks you tell kids to do in their very confined and comfortable environment of rooms, but it actually involves many, many cognitive steps. From the above, if you look at the previous task, what happened is this agent has to navigate to a different room, find the kind of object and tag it. You can also give it more detailed instructions, such as a diagonal stripe TV. So the agent has to look at all the TVs and tell the patterns, the difference in patterns, and oh, here, it's diagonal stripe. It goes there, types the diagonal stripe, and completes the task. It can even have two adjectives, red diagonal stripes. By the way, the grammar over here that the agent seems to understand is, again, not explicitly coded into the agent. The agent learns the grammar, learns how to parse English sentences by itself. And over here, we can actually let the agent output what it's thinking. When the agent is looking at that, say, oh, that's a call. So we can let the agent output the word because it's a computer system, so we can do all kind of tricks on that. We can't do that with humans, but we can do that with the agent, and we can actually tell what the agent is thinking about. Sometimes it's about color, sometimes it's about shape. But there is a way to translate what the agent is thinking into natural language. So this is like mind reading, but over an artificial intelligence system. So this kind of system is very advanced and is getting closer to a general system that people imagine. I wish I could show you the next video in the sequence, but we're not there yet because this video is only revealed last week, so the next one isn't out yet. But we can easily imagine this is only the agent roaming around in a simulated world within the confinement of two rooms. What if you break down the wall and let the agent go to a wider world where with all these like cityscapes, these looks like buildings, then the agent can learn more. What if you expand the vocabulary? Over here is probably just dozens of objects and a few grammars, but what if you expand the vocabulary? And the agent can learn more real English. Last December, in a conference, the lab that developed this system also reveals there was a more realistic environment where they actually simulated the natural landscapes. So with real plants and the soil and the water. I don't have the video because it wasn't public. But you could imagine that there will be agents that are being trained over this more natural landscape. And those natural landscapes are developed with the help of ecologists. They were procedurally generated and can have a lot of varieties. And if you extend this even further, what if we connect these type of agents with the internet? Then the understanding in language or its internal understanding of the world will be closer to reality. Again, we don't have the systems yet, so I have to do some imagination. I asked Google how to build a real-life AI like Jarvis. Jarvis is a voice-based artificial intelligent assistant that is featured in the movie Iron Man. And it's very smart, it has common sense, it has a plain interface that is voice-based, it can understand human languages, and it can do a lot of things just by itself over the internet. These are all technically possible except the thinking part. All these other structures are there. We have internet, we have chatbots. We just don't have chatbots that are that smart. When they are really smart, when you ask tough questions, for example, it can actually output things like, oh, this is how you go around building a real-life AI like Jarvis. Of course, Google doesn't know that. Google can only give a simple answer because somebody published news on that. And the news is about Mark Zuckerberg, who is the founder of Facebook, also looking at the same kind of thing, building a voice-based assistant. That's actually one sensible way of imagining AGI. A general AI can be just a chatbot, but talking sensibly and have the ability to think. Okay, this may not sound like a big deal. It's just one guy or one girl hiding behind machines. So what's the big deal about that? Well, the big deal over here is the generality of this intelligence. If you have 100 such chatbots or 1,000, they are not going to do the same thing because they are general. They can actually do different things. So even those intelligence, let's say they don't add up. Each of those little chatbots only is as smart as a person. And you have 3 chatbots, you can't add them up to say as smart or 3 times as smart as a person. Let's just say this doesn't happen. Okay, we are somehow at an optimum in intelligence, which is unlikely by the way, but let's just say it's the case. And we have 1,000 chatbots, what's gonna happen? Is that you have a personal consulting company working for you. Right? So having general intelligence is a big deal. And I'm going to extend that imagination a little bit over here. But a warning first, okay, there's no miracle. Even a super intelligence that is consisting of thousands of chatbots, they won't do magic. They can't pull an elephant out of thin air. Okay? They have to obey the rules in reality, but they can do a lot of amazing things. What if one chatbot is, say, let's write a novel, and another one composing music, and then a bunch of other chatbots, okay, let's generate pictures. Then you can automatically produce TV episodes without going through the traditional methods of hiring actors and actresses and directors. They can even be blockbuster movies. And when they are personalized and real time, they can become games. These are all possibilities that will be enabled when general intelligence is created. Think about education. If producing movies or videos, personalized videos, becomes very efficient, then we can actually produce education movies for all the kids, tailor-made for that particular kid's personality or character or performance or grade. That is going to cause a lot of changes in many industries. And I'm just talking about virtual worlds. I'm not even talking about real products. But real products and real work in the physical world is not immune either. Because think about it, if chatbots are that smart, if they can be creative in writing movies or music or movies or novels, then they can also do original scientific research. And that includes research in robotics. Meaning it wouldn't be that hard for them to eventually come up with a blueprint, say, let's make robots according to my blueprint. And you connect those robots to the cloud, you can get automated factories, We probably can even see buildings grow up from the ground. Well, these are magics from today, but we can imagine this happening once we have general intelligence that can learn and think like humans. We can even ask intelligence to solve today's hard problems, such as climate change, poverty, and disease. It can even help us understand ourselves. When artificial intelligence can do so many jobs that today require a lot of human expertise, that's going to raise the question of what's the meaning of our lives for many people. And when we see super smart machines, it's going to also reveal new insights about how intelligence works. It may even get to the stage where we ask what makes us human and what makes us unique. So we get to the deep philosophical realms of consciousness and personal identity. And this will be really exciting discoveries that we look forward to. So all these things, okay, the things I mentioned on this slide, they may sound very far-fetched, even science fiction. So why am I talking about this? If they're 100 years away, or even 50 years away, then there's no point in thinking too much about it, because it's just too far into the future. So we're going to get into the next topic, which is timing. Let's start with some expert predictions. There have been 3 large-scale surveys. One of the first surveys done was 5 years ago. So we had researchers connected with FHI, it's the Future of Humanity Institute. It's a research institute in Oxford focusing on, well, future of humanity, that's the name. They collected 170 responses from AI experts. They asked them a very simple question. When do you think when do you think there's a 50% chance that high-level machine intelligence will be created? By which year? That's the question they asked. They collected all the answers, and they find that the median answer back then was 2040. Okay, they were not supposed to use average. They can only use median, because some experts say it's never going to happen. So if you use average, then it's never going to happen. So you have to use median. That's the correct measure to use. Of course, some people don't agree with that. So there was a more recent survey done by AAI, that's the American Association of Artificial Intelligence. 80 experts about a year ago, and the conclusion was very simple. It's beyond foreseeable horizons. It's just very, very far into the future, almost impossible. You see, there is a divergence of expert opinions. Some people say, oh, it's happening. Some people say, no, it's not possible. So a larger survey was done more recently, about a year ago, by researchers from FHI, a smaller organization called AI Impacts that look at the AI's impacts on Yale. They collected 352 responses, and then they asked the same question. When do you think high-level machine intelligence will be created? There's a 50% chance that it's going to be created, and the median is 2061. It's more like a mixture of the previous one. By the way, the first survey was done 5 years ago, so that was before the recent explosion in deep learning. If you ask them today, I believe most of them would make the year even earlier towards the current time. Because, well, I'll just use an opinion from a Google co-founder, Sergey Brin. He stated in January at the World Economic Forum in Davos that Google is at the forefront of development of artificial intelligence, and he is very close to their research labs. And even he is surprised about the progress, positively surprised, because it's moving so fast. So if you ask those people today, they're likely to tell you the answer that's earlier than 2040. So this 2061 is more like a mixture of these 2 group of experts. Well, some of them overlap, but they clearly differ in their style because they give divergent opinions. But so I guess the simple picture is some experts believe it's going to come very, very soon, and some people believe it's close to impossible. I'm going to look at a few individual opinions that are more on the optimistic side. So Geoffrey Hinton is a retired professor at University of Toronto. He is very famous in the world of deep learning. He is considered one of the deep learning conspiracists, which I'm going to explain what it is later on. And he told media recently that he didn't say about general intelligence or high-level intelligence. He only pointed to common traits of those intelligence. One is common sense. And he said, okay, that's maybe just 10 years. But the reasoning may be a bit later, a little over 10 years from 2017. But those are the core challenges. and the core barriers from today's narrow AI system to the kind of general AI system. So that is actually a very optimistic forecast. Ray Kurzweil, who wrote a very popular book, The Singularity is Near, in 2005, and he predicted in that book that he would expect to see human level AI by 2029. In January, in a very high-profile conference in California, so this is after 12 years of new information, he reiterated that he feels the development is still on track to get to human level AI by 2029. Jürgen Schmidhuber is a German scientist living in Switzerland. He has been in the field of AI, and in particular deep learning, for a long time, decades. That was a really long time. For example, one of a very popular network module being used today, long short-term memory, is very widely used in many areas today. Okay, that was invented by him and his student 2 decades ago, 1997. So he obviously knows what's going on. He said in the same conference in January that he believed human level AI will be created before he retired. According to current Swiss law, that's 2028. He later gave another year, which is 2042. But the context is that this is assuming there is no new development in software. So if we just wait for the hardware to improve with enough computing power, speed, and memory and everything, then by 2042, we're going to get to the scale required for human brains. I'm going to show you an even more optimistic estimate. The reason I show this is because it was done many years ago, and it was a very famous prediction. Professor Werner Winch is a mathematician and also a science fiction writer. He actually helped popularize, he didn't come up with it, but he helped popularize the word singularity. He wrote 30 years ago, simply by extrapolating the trend of computing power in 30 years. No, sorry, he wrote in 1993 that in 30 years, which would mean 2023, that we would get to the computing system that rival human intelligence. And he said, we're on the edge of a change that's comparable to the rise of human life on Earth, because it's a huge deal if we could invent or create a machine that is as intelligent as human. So what is the scientific basis of that? It's actually not that hard. Even AGI is a big deal. The principle behind that is remarkably simple. We took a look at human brain a long time ago. People opened up the skull and see, oh, that's where we are so intelligent. That's why. Because it's just 100 billion neurons wired up and sending signals to each other. Why don't we just do that artificially? So this is a very simple idea. I'm going to use the words, again, from Alphabet. This is Alphabet chairman Eric Schmidt.
What we did not understand was that simple algorithms, or what appear to be simple algorithms, could replicate what were incredibly complicated taxonomies that had been designed by humans earlier. So the key thing is that large-scale simple analysis can appear to emulate very complex things.
Right, so, but...
Okay, so this is a very simple idea. If human brain is just about wiring neurons together, but lots and lots of them, then maybe scale is the key to intelligence. Let's just do that, and that is deep learning. It even has a name called prosaic AI, meaning that from what we understand today, it's plausible that we could scale up to general intelligence without qualitatively new understanding of how intelligence works. Any evidence? Let's look at here. So 2012, that's where everything started. Google Brain developed a large-scale computing system that recognized cats from YouTube videos. The system wasn't told explicitly to look for cats. It was just told to learn as much as possible, just look for patterns. And there was one neuron that's going to fire up every time you put a picture with cat in front of the system. A few months later, there was a more remarkable results. There was this ImageNet competition. It's a very prominent competition in the field of computer vision. Computer systems are asked to tell what's on the image. There are 1,000 possible answers, and they need to come up with the right answers. So the error rate is supposed to be really high if the computer don't know what to do. On this competition, usually the error rate went down 1% a year, from like 30% to 28%, 27, 26. But in that year, there was a new system entered this competition, and the error rate went down from 26% to 16%. And the team that submitted that new system were not even experts in computer vision. They don't know what are the fine definitions of cats, or desks, or tables, or things like that. All they need to know is all they understand, or they are experts in designing the kind of learning system that could look at the data and automatically extract the rules, so that they would do a lot better than engineers who try to solve the problems by their bare brain. It's like building an intellectual telescope and let the telescope get the useful information from the data, compared to other methods that use bare brain to go into the data themselves and extract the definition of 1,000 classes of different objects, and that made a difference. If you think about it, it's more remarkable results, but it doesn't mean harder work. It's as if you are asked to calculate the orbits of planets, there are experts that do this for many, many decades based on the assumption that the Earth is the center of the solar system. And you change your assumption, say, oh, actually, what if Sun is the center? You're going to use much easier calculations and get much more accurate results. It's not about being smart or working harder. It's about using the right kind of methods. It was actually very hard for the computer vision experts back then to expect this sudden change, because they were not looking at deep learning. And this is going to be true in the future as well. It's really hard to predict where the next milestone comes from. Let's take a look at a famous case of AlphaGo. By the end of 2014, DeepMind, the lab that developed all those nice video of games, it already put up a paper using neural networks to evaluate Go boards. It was published on Archive. Archive is a server of preprints. So many researchers put their work on Archive before they pass the peer review process. So it's public information. There's nothing in the hiding. Okay, and around mid-2015, it was also clear that it's relatively easy to build the kind of standard chess engine that can do tree search and optimize the moves. What they don't know is how to figure out Go, because in Go you have so many possibilities, and you need to go into the details to find out. You need to have some kind of Go intuition to understand where the moves. And that's also why progress in Go has been really, really slow. Even by the end of 2015, when Facebook came up with a neural network-based Go system that got to the level of 3D out of 90 in a Go rating scale, still the field wasn't impressed. Because if you look at the performance of Go systems, it went up very slowly from 1D to 2D to 3D. Even shortly before the famous matches between AlphaGo and World Champion Isabel, the mainstream opinion is still that the Go system won't be as good as human champions. Because if you look at the performance, the external performance of Go systems, it doesn't seem, it's hard for people to imagine that there is a huge change. We all know what happened later on. AlphaGo has proved in many occasions that it is a more superior player than human, at least in Go. One of the masters in China, after being beaten by AlphaGo, especially when he realized that AlphaGo is using moves that today's professional players don't understand, he felt a huge shock in his heart. You could imagine people who spend decades learning about Go, believing that they are getting close to the kind of optimal moves in Go, and suddenly realize everything is wrong, and that's what he wrote on microblog. One day, many years later, when you realize that everything you know is wrong, will you keep going down the wrong path or reject yourself? So this is the kind of difficulty people face in predicting where is the next milestone. Even the field experts, if you ask the professional Go players, or you ask the professional software developers in commercial Go systems, they wouldn't know this is coming because they are not looking at deep learning research. And similar things could happen in other fields or could happen for AGI. Because if we look at narrow AIs, it's really just one app at a time. But general AI is like all the apps at once, and that could be a sudden change. How do we look at that? Well, I guess the more reliable way is to look at where we are towards artificial general intelligence. Again, in that same conference in January, leaders from many of the labs that are on the forefront of AI development, they actually talked about how you'd go around and build human-level intelligence, and they listed some key points that have a lot of overlap. It's a bit hard to compare the columns, so I made another graph. This is what an AGI system would look like. You have an agent that has input and output. It thinks. You develop all kinds of neural network structures, modules, and learning algorithms. And if you put them together and you scale them up, then hopefully you're going to find that this agent can solve some of the challenges that are currently in the middle between today's narrow AI and the general AI. And when most of the challenges are solved, or even some of the key challenges are solved, we can get to the type of system that is general. So where we are today, well, this is a recent model that was developed by Google Brain. Again, it was published this month. And as you can see, it already has some of the very basic setups, like input and output. It can take in input in language, image, and audio. And it can do multiple tasks, such as looking at an image, not just tell what's on the image, but actually comes up with a description in natural language, like one guy standing in front of a full room, something like that. It can also translate between English, French, English, and German, and it's done in one model. It's not like 8 different apps for 8 different tasks. It's one model. In fact, by learning vision, by learning how to classify images, the researchers found out that it actually helped with translation and language tasks. So there's really some internal consistency inside the model that is one coherent model that's doing all the tasks. Steps like this happen very quickly. If you look at today's AI, yeah, we're very far away. There are many, many challenges. But that multi-model is only one of the steps that happen over here. It's one model to learn them all. And steps like that, concrete progress towards artificial general intelligence happens at unprecedented speed. These are all research results that are published this month. I'm not talking about historically. If you look at 706, that means this month. And all of them attacked one problem or another towards artificial intelligence. So if you look at external performance, we may be very far away from general intelligence, but that doesn't translate necessarily to a long time lag because we are progressing really, really fast. So what should we do? Let's take a look at what other people are doing. First, the financial market. The red line is NASDAQ, the blue one is S&P, that's the broad market. Well, there are AIs betting on stocks, so maybe the AIs are already betting on themselves, the future of AI, because we know NASDAQ is tech heavy. If you look at the current most valuable companies, a list of the top 10 companies in market cap, 7 out of 10 are technology companies. And what did they do in the past? They invested heavily in AI technology. Google started this whole thing in June 2012 by recognizing cats. And then later on, when the ImageNet, when the team from Toronto won ImageNet, Google acquired a company funded by them for reportedly $50 million US. That was early 2013. It's even before most people realized there was something going on. DeepMind, the lab that develops the video game system, Facebook tried to acquire DeepMind, but it failed, and Google acquired it in early 2014 for £400 million. And as Facebook failed to acquire it, it hired one of the deep learning conspiracists, Professor Ian LeCun, to lead its own internal AI effort. With the financial backing of Google, DeepMind acquired 2 smaller companies, Dark Blue Labs and Vision Factory. One is on natural language processing and the other is on vision, so that makes a more complete setup of a modern AI lab. Elon Musk was an early investor. Actually, Li Ka-shing is also an early investor. But Elon Musk, being an early investor of DeepMind, after he was bought out by Google, he used his money and pulled some more money from his buddies and funded a general AI lab called OpenAI by the end of 2015 with $1 billion. So all these giants, they're pouring money into this. And this is just general AI efforts. I'm not even talking about narrow AI efforts. And those are even bigger efforts because you can easily make applications. These are just general AI. the leading industry labs, because there is so much money poured into this, there's a brain drain from academia to industry. The best talents today they all reside in the industry. Google Brain and DeepMind, they all have their focus on solving intelligence. So is Facebook. OpenAI makes the goal even more explicit. It says, build safe AGI and ensure AGI's benefits are shared. When OpenAI was founded, it didn't even put up AGI as a word. Because less than 2 years ago, when you talk about the AGI, most people think you are nuts. So if you are serious researchers and you talk about, oh, we're doing research in AGI, then there is a risk that you'll be considered crackpot scientists. It's not the case anymore. A serious research lab backed by over $1 billion put AGI up there very prominently. That's what we do, because the progress has caused a change in perception on where we are in the field. There are smaller labs. Microsoft, Baidu, Tencent, all the giants are in this game. I'll take a closer look at Alphabet because the first two labs in my previous slide, Google Brain and DeepMind, they're all under the same parent, Alphabet. And what do they do? Since 2014, each of the labs has published more than 200 papers. DeepMind has AlphaGo, which we all heard about. Google Brain developed